Good morning, everybody. So what we're going to be doing today is we're going to be finishing the discrete Fourier transform. We're going to be looking at the properties of the discrete Fourier transform, and we're going to be introducing the circular convolution and relating it to the discrete Fourier transform. And before we look at the properties, we're going to look at the discrete Fourier transform of sinusoidal signals. Okay, so if you have a continuous time signal, and that continuous time is x of t equal to cosine omega 0 multiplied by t. Then we know the Fourier transform of this signal is going to look like two impulses at omega 0 and negative omega 0. And the magnitude of the xc of j omega is going to equal to a pi and a pi. Now if you take this continuous time signal and we convert it to a discrete time signal, so if we have a discrete time sinusoidal signal, so if you look at the discrete time sinusoidal signal, the spectrum of this signal, if we take the discrete time Fourier transform, is going to look something like this. I'm going to have an impulse at omega 0. This is omega. And I'm going to have another impulse at negative omega 0. This is x of e to j omega. Okay. Now both of these signals are assumed to go from negative infinity to infinity. So this is a sinusoidal signal that goes from negative infinity to infinity. This is a sinusoidal signal that also goes from negative infinity to infinity. Now if I have a sinusoidal signal that exists for a finite amount of time, then I have to calculate the windowed discrete time sinusoidal signal, or the spectrum of the windowed And in this case, we have xw of n equal to w of n multiplied by cosine omega 0 n. Does that make sense? So in this case, this signal only exists for a finite amount of time, depending on the window that we choose. This is the width of W of n. How does the discrete time Fourier transform of this signal look like? Anybody want to guess? If this window is a rectangular pulse, it's the same. And if I multiply the window with the sinusoidal signal, in the frequency domain, it's going to be the convolution of the two. So therefore, the spectrum is going to look something like this. Okay. Now, assuming we have a rectangular pulse, then this width is going to equal to 4 pi divided by L for a rectangular pulse. So the wider the rectangular pulse that we choose, the wider the window, the narrower this thing is going to be. Okay. Now what happens? So this is xw of e to j omega. What happens if we plot this DFT of this signal? The DFT is going to be a frequency sample discrete time Fourier transform. So therefore, the spectrum is going to look something like this. Okay. Now the distance between two samples, delta omega, is going to equal to 2 pi divided by n. And therefore, as we can see, for the appearance of the discrete Fourier transform, as n increases, we have more resolution of DFT plot, DFT. Okay. Let me ask you a question. Why is it important to have a higher resolution? What is the impact of the resolution when I'm plotting the spectrum?
It makes it more visible.
Correct. So what it does, as we're going to see when we run the MATLAB, okay, so this is an example of the spectrum of the sinusoidal signal. We have a sinusoidal signal, and the frequency of the sinusoidal signal is equal to 0.22, and this is, we're seeing these two spikes at that frequency. Sorry. Just copy this. Okay. Now what we're going to also run is we're going to run another script where we have two sinusoidal signals. And I'm going to run this with n equal to 16. Run it with 32. So what we have here, we have two sinusoidal signals. And you can see when I add these two sinusoidal signals, depending on the resolution, when I generated the sinus, I have two sinusoidals. One has a frequency of 0.22, one that has a 0.24. And I'm adding them together. Now, if I choose n to be very small, I'm not going to be able to separate these from each other. So, for instance, n equal to 16, it looks like I have only one sinusoidal signal, which is this and that. However, if I increase n, if I have n that is equal to 1024 and I run it, you can see now that I can see clearly the two signals here, the two sinusoids. So therefore, if I have a signal and I'm trying to study and analyze this signal, and I know this signal is made up of many frequencies, I have to choose n large enough in order to be able to differentiate the different frequencies. Make sense? Okay. Finally, before we look at the properties, I want to run an example. So let's say that we have a voice that is recorded that I want to plot the discrete Fourier transform for. So I have a voice signal. So this is the time domain, and this is my signal. And I want to use MATLAB to plot the spectrum of this voice, similar to what you guys are doing in the project. So what is the first thing we're going to do? We're going to sample this signal. And therefore, we're going to get a discrete time signal. So once we record this signal, it's already in discrete form. Of course, this could be positive or negative, it doesn't matter. Okay, so let's say that we sample this signal at a rate such that f sampling is equal to 8,000 hertz. And let's say that the length of this sequence of the signal that I have is 512. So when I go and use MATLAB and ask MATLAB to plot the spectrum for this signal, MATLAB is going to plot something like this for me. So this is the FFT of MATLAB with the shift. It's going to plot a spectrum that's going to look something like this, something like this. Okay. So this is going to correspond. So the length of this sequence, what is the length of this sequence going to be equal to? 512, unless I specify a different number. $512. So therefore, the first index is going to be at 256, and the last index is going to be at 255. Now this corresponds to negative pi, and this corresponds to a pi, because this is our discrete signal. The frequency range is from negative pi to a pi. But omega is equal to W multiplied by T, which is going to equal to therefore omega is equal to, or W is equal to omega divided by T, which is going to equal to a pi, a plus or minus pi, multiplied by 8,000. And therefore, the frequency is going to be plus or minus, I'm going to divide by 2 pi, 4,000. And therefore, if I want to plot this against the frequency, which we often do, so if I'm going to label this as a frequency, this value here is going to be minus 4,000, and this value here is going to equal to 4,000. Does that make sense? And this is what the centered FFT does in the function centered FFT. It will return the frequency, and this is how it generates the frequency. Depending on the length, it's going to divide it into 2, and depending on the sampling frequency, this is going to correspond to negative pi, and that is to a pi, and then multiplied by the sampling frequency is going to give me the frequency range to plot the spectrum of the signal. So let's look at an example. Okay. So here is the audio signal, and this is the discrete Fourier transform of that signal. Now, because this signal is sampled at 8 kilohertz, then the range that I'm going to plot the spectrum for is going to be from negative 4,000 to 4,000. Does that make sense, everybody? Okay. With that, we are ready to look at the properties of the discrete Fourier transform. So the first property is linearity. So if I have a sequence x of n, sequence 1 that has a length that is equal to n1, and I have x2 of n that has a length that is equal to n2, then if I create a new sequence, if x3 of n is equal to a x1 of n plus b x2 of n, then the discrete Fourier transform of x3 of n is going to equal to a multiplied by the discrete Fourier transform of x1 of k, x3 of k, plus b multiplied by x2 of k, where x1 of k is the endpoint DFT of x1, and x2 of k is the endpoint DFT of x2 of n. And where n is greater than or equal the maximum of n1 and n2 in order to avoid aliasing.
You didn't subscript your ends. Or wait, no, in brackets, just
Okay. Okay. The next property is the circular shift. or the time translation. Now, in the discrete Fourier transform, discrete time Fourier transform, if I have a sequence x of n that has a discrete time Fourier transform x of e to j omega, then if I shift, bless you, x of n by m, the discrete time Fourier transform is going to equal e to negative j omega multiplied by m multiplied by x of e to j omega. So basically the slope here is equal to negative m, which is equal to the shift that we've done to the signal. Now we're going to see what this corresponds to in the discrete Fourier transform. So again, this applies to the discrete time Fourier transform. So let's see what happens with the discrete Fourier transform. So in the discrete Fourier transform, in order to introduce the circular shift, we have to introduce, or we have to define the circular shift. And in the circular shift, if we have an endpoint sequence, and this sequence is shifted by m, then the m values of x of n that would shift beyond n minus 1 will get wrapped around to 0. Okay. So for the discrete time Fourier transform, again, this is a linear shift. This shift here is a linear shift. A linear shift will result in this exponential term with a slope that is equal to the linear shift that we've done. Now we want to study the discrete Fourier transform. And therefore, to do the property for the discrete Fourier transform, we have to introduce a new shift, which is called circular shift. Now, this circular shift is the symbols or the notation we use is x of n minus m, capital N, or x of n minus m. And what this means, you shift the signal by m, and any signal that is beyond n minus 1, you're going to take it and you're going to bring it back, and it's going to become indexed at n equal to 0. So let's see how this works. So as an example, if I have x of n, and this is n, and x of n is 0, 1, 2, 3, 4, and 5. And for this signal, n is equal to 6. Now if I do x of n minus a 3, I'm going to shift this signal. So it starts at 3. 2, 3, 4, 5, and 6. Now, if I want to calculate the circular shift of x, I want to calculate x of n minus 3 to the 6th. I'm going to go to any point that is beyond 6 minus 1, which is 5. And I'm going to take them and I'm going to move them back to here. So therefore, a 0, 1, 2, 3, 4, 5, 6, 7, and 8. These points are going to be shifted and moved to the 0. Does that make sense? So x of n minus 3 with n equal to 6. We're going to shift the signal by 3. And then we're going to go to 6 minus 1, which is 5. Any signals beyond 6 minus 1, which is the 5, I'm going to take it. And I'm going to move it back to the index of 0. Okay. Now you can see that when we do, if I have a signal that has a length of, for instance, 6 from 0 to 5, if I do a regular shift, then this signal is going to go outside the window from 0 to 5. But if I do a circular shift, the signal, still all the signal components are defined between 0 and 5. Okay, so with that circular shift, we can define the property that corresponds to the property of the shift in the discrete time Fourier transform. So in the discrete Fourier transform, the circular shift property says the following. If you have x of n, and x of n has a discrete Fourier transform that is x of k, then if you do a circular shift on x of n, then the circular shifted signal is going to have a discrete Fourier transform that is equal e to negative j 2 pi k multiplied by m divided by n multiplied by x of k. So unlike the discrete time Fourier transform where if you have a linear shift, you're going to have an expression similar to this. With the discrete Fourier transform, the circular shift will give you that phase that results from the circular shift. A note here, if we zero pad if zero padding is used so that L plus M is less than or equal to N, then a circular shift is going to be equal to the regular shift. Okay, So for example, if I have a sequence that looks like this, 0, 1, 2, so the length of the signal is a 3, and I'm going to shift it by 2, and n is equal to 5. So 5 is greater than or equal to 3 plus 2. Then if I put, this is x of n, if I plot x of n minus 2 to the 5, I'm going to shift the signal by 2, 1, 2, so therefore I'm going to have the signal looking something like this. Anything beyond the 4, I'm going to take it and shift it back, but there is nothing beyond the 4. So this becomes similar to the linear shift. So here I'm going to take this signal, move it back to here. Okay. Does that make sense? So a circular convolution of the signal will give me an exponential multiplied by the discrete Fourier transform. The next property is the circular convolution property. So in the normal discrete time convolution, which is the linear convolution, if I have x1 of n and it is defined between 0 and m1 minus 1, and therefore it has a length of m1, and I have another signal x2 of n defined between 0 and m2 minus 1, and it has a length of m2, then we can do the convolution to get x3 of n, which is going to equal to x1 of n, convolve with x2 of n, which is going to equal the summation from m equals 0 to m2 minus 1 x2 of m multiplied by x1 of n minus m. And we're going to do that for n between 0 and less than m1 plus m2 minus 1 minus 2. So the overall length is going to be m1 plus m2 minus 1. Okay. So this is the linear convolution, and I think we've probably done an example at the beginning of the course on that, and we'll do another example in a minute. In the circular convolution, we use circular shift. And therefore, if I want to calculate x of n equal x1 of n, circularly shifted with x2 of n, or circularly convolved with x2 of n, this is going to equal the summation from 0 to n minus 1, x1 of m, x2 of n minus m,
Wait,
and n, go ahead.
why is at the top of summation m2 minus 1? What about m1?
From 0, because it has a length of m2.
Okay.
This one has a length of m2. This is m1. So the length, are you objecting to the negative one?
Just what about the first?
Or we can do it either, depending on like which term you have here.
Okay.
Does that make sense? x1, x2, you can flip them and do it to m1. Oh, I see what you're saying, because I'm shifting m1. I'm shifting in, yeah, this might be m1. Okay. Actually, no, I'll take that back. This is 2 minus 1. I'm keeping x2, and I'm shifting x1. The only terms that are not going to be 0 are the ones that are going to overlap. And they're going to be from 0 to m2 minus 1. Okay. Again, here, we're keeping m2, we're shifting x1. So if there is overlap, we have values. If there is no overlap, the terms are going to be 0. So the only time we're not going to have an overlap is between 0 and m2 minus 1, which is where x2 is defined. Okay. So few observations on the circular shift. So the first thing is the circular convolution, depends on the choice of n. The length of the convolution output is going to equal to n. N must be greater than the maximum of m1 and m2. And if n is greater than or equal to m1 plus m2 minus 1, then the circular convolution is going to equal the linear convolution. Okay, so with all that, let's see how we can perform the circular convolution. And we'll see why this also circular convolution is important. Okay. Okay, so let's do an example on the calculation of the convolution. And let's say we have a signal x1 of n, which is defined as the following. It is a 1, a 2, a 3, and a 4. A 2, a 3, and a 4. 0, 1, 2, and 3. And another signal, x2 of n, and it has a value of 2, at 0, and then a 3, and then a 1. Two, 3, and a 1. Okay, so x1 has a length that is equal to a 4. x2 of n has a length that is equal to a 3. So we're going to do both linear convolution and we're going to do circular convolution. So first we're going to calculate x1 of n. This is linear convolution of x2 of n. How we do the convolution? Anybody still remembers? We can do a table, but we can even do something better than a table. So we calculate how long the sequence of the output is going to be, which is going to be the length of the n1 plus n2 minus 1. And then what we're going to do is we're going to generate a matrix of the first signal, which is 1, 2, 3, and 4, and then 0 and 0, padded with zeros. Then we're going to shift this down, 1, 2, 3, and 4, and 0. Then shift it again, 0, 0, 1, 2, 3, and 4. Then shift it 0, 0, 0, 1, 2, and 3. 0, 0, 0, 0, 1, and 2. 0, 0, 0, 0, 0, and 1. And then the second signal is 2, 3, 1, 0, 0, 0. So this is 6 by 6. This is 6 by 1. And this is going to be 6 by 1. Okay, so we could have done the table, which is equivalent to this. So we're going to take the first sequence, then we're going to push it 1 and put it here. Push it 1, and what comes in is a 0. So we're not rotating, we're just pushing in. Okay, so if we multiply it, we're going to get a 2, a 7, a 13, a 19, a 15, and a 4. So this is our linear convolution. Next, we're going to do circular convolution. And we're going to do circular convolution with n that is equal to a 4. Since n is equal to a 4, we're going to do the same thing. We're going to create this matrix that is going to be 4 by 4. And we're going to have 1, 2, 3, and 4. However, now we're going to push down and it's going to bring it up to the top. So it's going to be 4, 1, 2, 3. Push again, 3, 4, 1, 2. Push again, 2, 3, 4, and 1. And then we're going to multiply it by 2, 3, 1, and 0. And this is going to give me 17, 11, 13, and 19. Okay. Let's do it with n equal to a 5. Very similar. We're going to establish a 5 by 5 matrix. 1, 2, 3, 4, 0. 0, 1, 2, 3, 4. 4, 0, 1, 2, 3. 3, 4. 0, 1, 2. 2, 3, 4, 0, 1. 2, 3, 1, 0, 0. And we get 6, 7, 13, 19, and 15. So this is circular convolution with n equal to 5. Let's do circular convolution with n equal to 6. I'm going to get 1, 2, 3, 4, 0, 0, 0, 1, 2, 3, 4, 0, 0, 0, 1, 2, 3, 4, 4, 0, 0, 1, 2, 3, 3, 4, 0, 0, 1, 2, 2, 3, 4, 0, 0, 1, and multiplied by 2, 3, 1, 0, 0. Okay. And if you do that, we're going to get 2, 7, 13, 19, 15, and 4. What do we notice?
There's a 0 missing in the second matrix.
A 0 missing. What else we notice? It's similar to the linear. Yes, excellent. This is the same result we got with the linear. So this, in this case, since n is equal to m1 plus m2 minus 1, the circular convolution is equal to the linear convolution. Okay. I'm going to put greater than or equal. It is equal, but in general, if it is greater than or equal, it's going to be equal. Okay. Ask.
Can we look at the matrices for linear?
Mhm.
And that's supposed to be all zeros
Mhm.
in the top right.
Yeah. Yeah, these are different. Remember, there's the multiplication, the results are the same.
Okay, I'm good.
Okay. So with that, now that we have introduced the circular convolution, we can look at the circular convolution property, and we'll see how we use this property. So what this property says, if you have x1 of n, and x1 of n has a discrete Fourier transform that is x1 of k, and you have x2 of n, and it has a discrete Fourier transform that is x2 of k. Both of these are endpoint DFT. Then x1 of n circularly convolved with x2 of n is going to have a discrete Fourier transform that is x1 of k multiplied by x2 of k. Okay, so this is the case of DFT. In the case of discrete time Fourier transform, DTFT, x1 of n has x1 of e to j omega, x2 of n has a discrete time Fourier transform x2 of e to j omega, then x1 of n convolved with x2 of n is going to have a discrete time Fourier transform that is x1 of e to j omega multiplied by x2 of e to j omega. Make sense, everybody? So unlike in the discrete time Fourier transform, in the discrete time, if I do convolution in the time domain, it's equal to the multiplication of the discrete time Fourier transform. In the discrete Fourier transform, if I do circular convolution, the discrete Fourier transform is going to be the multiplication. Okay.
Got a subscript 2 on the DFT.
Yeah, x2. Okay. So let's look at the application of this. So application FIR filtering using the discrete Fourier transform. So what we're going to do here, so for FIR filter, the output y of n of the filter is going to equal the summation from m equals 0 to m h of m x of n minus n. What is this equal to? The convolution. If I have the frequency response of the filter, of the FIR filter, because the FIR filter has a finite impulse response, I can take h of m and convolve it with any input signal to get the output of that filter. Make sense? What is the length of this filter in this case? N plus 1. Because I have from 0 to n. Okay. Now also we've seen if you choose n large enough, then linear convolution can be done via n-length circular convolution. We also saw that circular convolution can be done via discrete Fourier transform. So therefore, from 1 and 2, FIR filtering can be done using discrete Fourier transform. Together? So again, if we choose n large enough, the circular convolution is equal to the linear convolution. And we looked at the circular convolution property. We said we can evaluate the circular convolution using the discrete Fourier transform. Where was that property? Here. Circular convolution. Here's the circular convolution, the multiplication of x1. The circular convolution is going to give me the multiplication of x1 and x2. Yeah. The circular convolution is going to give me x1 multiplied by x2. What does all this means? So let's put it all together and do an example. So what we want to do is I want to do the filtering of the FIR filter. So therefore, I'm given h of n, a signal x of n, that is defined between n equals 0 and L minus 1. This is of length that is equal to L. And also I'm given h of n that is between n equals 0 to p minus 1, and therefore it has a length that is equal to a p. P is equal to m plus 1, where m is the filter order. Okay. I'm going to take this off. That's length of a p. Now we're going to select n to be greater than or equal to L plus p minus 1. And I'm going to form a 0 padded sequence of length n. So therefore, I'm going to form x hat of n that is going to equal to x of 0, x of 1, all the way to x of L minus 1, and then 0, 0, all the way to zeros. So here I'm going to have n minus L zeros. And similarly, I'm going to calculate h hat of n, which is going to equal to h of 0, h of 1, h of m, and then 0, 0, 0, 0. So here I have n minus p zeros padded, and m is equal to p minus 1. Good? Okay. The third step, I'm going to calculate endpoint DFT of x hat of n. This is going to give me x hat of k. I'm going to calculate that the discrete Fourier transform of h hat of n. This is going to give me h of k. And then I'm going to multiply, or I'm going to compute y hat of k, which is equal to x hat of k multiplied by h hat of k. And finally, I'm going to take the inverse discrete Fourier transform. Y hat of k is going to give me y hat of n. Last step, the first L plus P minus 1 terms of y hat of n are equal to x of n convolved with h of n equal to y of n. Does that make sense? So we can, if we're going to do a convolution, we can do either the convolution using the method that we know, or this is the new method, which tells you take x, the signal you want to convolve, take h, pad them with zeros, then calculate the discrete Fourier transform for them, multiply them together, then take the inverse for discrete Fourier transform. What do you think the implicit assumption here is that make all that possible? The implicit assumption is that there is an efficient way, a very efficient way of calculating the discrete Fourier transform. Does that make sense? So we're saying the discrete Fourier transform, we can calculate it very efficiently. So if I do a convolution, why don't you just use this discrete Fourier transform because we can calculate it very efficiently. Okay, let's do an example. Let me run MATLAB and show you an example. Okay. And this is the example that we're going to see. So if you look at the code here, I have two signals, x1 and x2. I padded them with zeros. I'm going to calculate the convolution of x1, x2 in one graph. And in the second graph, what I'm going to do, I'm going to calculate the DFT of x1 multiplied by the discrete Fourier transform of x2. Then I'm going to take the inverse discrete Fourier transform and put it in x. I'm going to plot them, and as you would expect, both of them are going to give me the same results. You should always clear all and close all. Both of them give me the same results. Make sense? So this is using the inverse FFT, which we said is the same as DFT in MATLAB. And this is using the convolution of the two sequences. Now again, the implicit assumption of why we've done all this, that we should clarify, is that why will we use this DFT? Because DFT can be calculated very efficiently using fast Fourier transform. So therefore, we can perform FIR filtering using many less computation than evaluating the convolution of the two sequences together. Any questions? Okay, so this is our last lecture in class. Now what I'm going to do, I'm going to record a lecture about FFT, the fast Fourier transform, because here I'm claiming that we can do the calculation of the DFT very efficiently using fast Fourier transform. So we'll have a lecture, a recorded lecture that will cover the FFT, or at least it will give you a flavor of what this FFT means and how you can do this calculation much more efficiently. Sounds good? Thank you, everybody. Good luck to those who are graduating, and wishes to those who are not graduating. Any questions, Fort Walton? Okay. Thank you, everybody. Now today, this is our 27th lecture, again, because we took 2 lectures during the exams. That gives us like the 2 lectures that we can cancel next week. But nevertheless, I'll add also the recorded lecture that covers the efficient calculation of the DFT.